Yeah, hi everyone. This is our demonstration of SBAS, the secure backbone AS, which serves as a secure underlay for the internet. And what SBAS is basically like a secure backbone network that acts to the outside as a regular autonomous system in the internet, connecting to other existing autonomous systems like Google, Apple, Microsoft, or also internet service providers. So the idea behind the secure backbone is to like create or improve security and also performance in parts of the network without changing like the whole network. So they can fundamentally eliminate the threat of, for example, routing attacks. So in addition to SCION, a next generation internet architecture, there's also BGP-SEC, which allows to eliminate these attacks, but BGP-SEC is not globally deployed. And also SCION is at the moment only offered as a commercial service by some ISPs. So the point is legacy clients that do not have access to both of them get no benefits of these security features. So with SBAS, we want to answer the question, can we extend the security benefits of even a limited secure backbone deployment to the broader internet? So before I want to answer this question, let me give you a short overview of SCION. So SCION is the next generation internet architecture that is based on the concept of path-aware networking. It consists of a control plane and a data plane. And the task of the control plane is to construct so-called path segments, meaning a specific segment of networks in the internet. And these path segments are then exchanged between participants in the internet. And in the data plane, these path segments can be constructed to end-to-end paths. And each packet in SCION contains the full end-to-end path in an encoded fashion, so that end hosts and applications can fully influence the forwarding in the internet. And furthermore, this also makes router operation easier. So like the routing operation itself is simple, and it's a stateless operation to forward a packet because everything is inside of the path. So for SBAS, it's basically like a secure backbone AS that to the outside looks like a regular AS, and it uses SCION as a backbone. So it can, so with SCION, it also like improves security of the deployment, and it can optimize, for example, for latency, for CO2. It's transparent to internet hosts. So if I connect to this backbone AS, I don't see that from outside that it runs SCION. It just looks like a regular AS. And the key point is that we don't need to upgrade like source or destination by connecting to the backbone AS. And what we want to do in this project is to deploy SBAS in the education and research network that we are running at the moment. This consists of several ASs in 3 major regions, US, EU, and Asia. And we have already deployed some points of presence, so entry points into the backbone AS, and we are these are the green ones, and we are currently still continuing to deploy more points of presence. And to each of these points of presence, there's like customers can connect to the AS to kind of use the services of secure backbone routing. So we see that SCION benefits can become available to hundreds of thousands of internet users by making them available to all of the researchers and students in all of these universities. And in this project, we want to show the SBAS enhancements in terms of security, privacy, and performance. So with this, I want to start like with the first part of the demonstration, so the actual deployment in the SCION education and research network. So here we can see 2 terminals, like the left one on the Equinix machine, 1 point of presence, and the other one here at our University of Magdeburg. So SBAS consists of some services that are usually installed via systemd. So the first one is the SBAS service that runs like the route dissemination path selection mechanisms and so on. And the second one is the SCION IP gateway, which basically translates SCION and IP packets and vice versa. And this IP gateway is regularly configured by a file called sig.json, which is automatically generated by the SBAS service. And this file contains a mapping from SCION AS numbers, for example this one here, to IP subnets that are accessible over this AS number. For example, this subnet here. And this is used to announce like own routes and customer routes to other participants, so that these can be exchanged. So at first, let's have a look at regular SCION connectivity. As a path-aware network architecture, SCION offers a mechanism called show paths that just creates all the available end-to-end paths between two destinations. In this case, we have like a direct one-hop path between our AS and Equinix. And SCION also offers a utility to do a SCION ping that actually is like the equivalent of a regular ping, but just over SCION. So it has an interactive mode so that you can actually choose the paths. In this case, we only have one path. So we will choose this one, and we can see that it sends sequence numbers and measures the actual round trip time. Next, I want to show a thing that is called the SCION IP gateway routing table. So this contains like the actually obtained routes and paths to all the other points of presence that are running. So there's a control plane exchange mechanisms to fill this table according like based on the configuration that we did. So we can see here the other remote ASs, like their status, they are all healthy, and we can see the path that are chosen. Like, and here down we can also see the routing table again. So like the actual paths, the next hops, and so on. So this is like the core part that is required to announce and to forward over these routes here. So we can also check like the IP configuration. So SBAS usually for each connected point of presence creates like an own interface. For example, we can see here to our connected Equinix point of presence that we have like an own interface with a given MTU, which shows like our own IP and the peer IP. So these are basically point-to-point connections between all the POPs. And yeah, what SBAS actually offers is regular IP connectivity over SCION. So if we want to speak to Equinix, we can just ping like one host in the remote network via a regular IP ping. This is then translated to SCION, transferred over the SCION network, and then translated back to regular IP traffic. And this can be also done with customer routes and customer networks. So SBAS consists also of a BGP side that we can inspect, and it can connect to existing BGP ASs just as a regular AS. So we can, it uses BERT internally to run BGP routing. And we can also have a look at the BERT configuration. So what is interesting is that we have like an eBGP configuration of all the routes that are announced to customers. So all the routes that the SBAS POP gets from its neighbors and also from the customers of its neighbors. And it runs iBGP to disseminate routes between all the connected points of presence. This is basically like the main part of the routing configuration, so that the POPs ensure connectivity between each others, and that all the announced routes of all customers are also forwarded to the customers of all other points of presence. Yeah, and of course we can also ping backwards from Equinix to OFGU. So connectivity is of course working in both directions. Yeah, that's the first part of this demonstration, showing the actual deployment of SBAS in the education domain. Okay, great. Then let me continue with the second part of the demonstration, which is about SBAS security in the SEED Internet emulator. So the SEED emulator is basically a tool that allows to run containers to recreate internet security or performance measurements in an emulated setup. So it creates containers and Docker networks out of a given topology that you can code in Python, and it allows you to run your experiments. So what we did here is we recreated the Sierra topology in the emulator. So you could see here like a map here, and it's a bit more detailed than the picture that we have, because it also contains router nodes and internet exchanges, which are the stars and so on. So you can filter for expressions here, replay stuff, and also connect to all kind of containers. So border routers, control services from SCION and everything. Like you can see the IP addresses, you can see the internal networks that are used. It's a really great tool for conducting like experiments. And yeah, what we want to do is like to show that SBAS is like resilient against hijacking attacks. So we have like one node in a customer AS that connects to the SBAS instance that we deployed. We recreated the same instance here in the emulator. And yeah, so we have like another customer that offers a given IP subnet, and we want like to ping like a host in this network. So we can see that it works. So like for showing that this kind of experiment don't work, like this kind of hijacking does not work for SCION, we can also like connect to this host via a SCION network. So it's basically connecting to a point of presence that could, if it was not included in the SBAS deployment, could be hijacked otherwise. So we can also do like a SCION ping. The command looks a bit different, but in theory it's the same. So we can, as we saw before, choose between paths. Here we have like a more versatile list of paths, and we just want to use this first one. So we have like a bit of latency overhead, but it's not the main thing that we would like to consider here. So as we can see, like BGP connectivity is working, and also SCION connectivity is working. So what we want to do now is to start the hijacking. So we have prepared a script for this, so that just waits for the input. So we can press enter, and it's starting to hijack like the ASs. So if we run the regular ping, what we now observe is that our traffic is obviously not reaching our given destination. It's rather was hijacked by another AS with the AS number 11. So like this is a regular example of hijacking an insecure BGP route. And what we want to show here is that in SCION this is not affected. So inside of the backbone, we can still use like the same SCION ping to reach this host, so it's not affected by any BGP related routing attacks. And yeah, that's basically what we wanted to show with this emulator. So like performing hijacking experiments in a real world internet would probably cause a lot of harm, and it's just not intended to do this. Like security experiments are great for like emulated or virtualized setups, but yeah, in practice you don't want to do this because you could harm people. So yeah, that's what we wanted to show here, which is really great. So for the hijack, we could also see how we perform the hijack. So we connect to AS number 11, and here let me double check this router here. And similar to like our real world SBAS implementation, it uses BERT under the hood. And yeah, what we can see here is that this AES maliciously announces like routes from the other AES, and this is what like makes the AES hijacking attack possible, and this is what we can avoid by deploying SCION as a secure underlay backbone.